Hello, everybody. Welcome to week three. Today, we are going to be talking about hypothesis testing. So, I am certain if you made it this far along that you have at least heard the term hypothesis testing, even if you don't, you've never actually done it before, or you don't fully understand what exactly it means. I'm sure you've heard the term, and I'm sure you've heard the term, well, things like statistical significance. Significance, that's used a lot in media. I'm sure you've heard what a p-value is. So that's going to be the topic of today is this idea of statistical significance, and what that means, what p-values mean, and how we arrive at it. So fundamentally, with statistics, we have one thing. We're always trying to gather one thing. The thing that we're always trying to gather is evidence. And we want evidence. We want to know, do we have sufficient evidence to draw a conclusion, right? Just do we have sufficient evidence to draw a conclusion? Um, so obviously, evidence is not a black and white issue. There's shades of gray for evidence, right? And there's often contradictory evidence. But we need to look at, if you're like a lawyer, what the preponderance of the evidence is, or what beyond a reasonable doubt is. That you have to look at the evidence and weigh it in some way, and you have to fundamentally come to a conclusion, because the world works when you come to some kind of conclusion. And we want to come up with a conclusion that takes this, inherently gray situation, right? So evidence is an inherently gray, non-black and white issue. And we want it to come with a conclusion that either yes, we do have sufficient evidence, or no, we do not have sufficient evidence. Okay, and that's what hypothesis testing has. Uh, uh, that's what hypothesis testing does. It's a agreed upon procedure within the scientific community for taking something that's inherently uh, not black and white and making it black and white. Either yes, you have sufficient evidence, or you don't. No, you don't have sufficient evidence. And I say that it's agreed upon because it really is. It's really a social construction, right? It is just norms and tradition are what guides this, right? Right? Norms and traditions tell us how we should proceed in order to do this. Um, there is some validity to it, but things like a p-value being less than 0.005, well, that's nothing more than something that was proposed in the 1920s that has stuck. Okay, so it really is, hypothesis testing. What I like to say is hypothesis testing really is a social construction, right? Right. The social construction being that society has created a way to arrive at decision making, although there could be another society that would come up with a different set of procedures to come up with decision making to see if there's sufficient evidence. All right, I imagine that if an alien planet, they probably wouldn't come up with the same exact procedure to weigh the evidence as we do. But nonetheless, we are bound to it in our research. So we've seen this a little bit, right? So we came up with this, or we talked about it at least, that, well, wouldn't it be nice? So last week we were looking at confidence intervals, and we asked ourselves, okay, in Maine, it appeared that in Maine we had about twice the national rate. So here's our Maine prevalence rate of tuberculosis, and it was about twice the national average. And so we wanted to come up with a confidence interval for this. So the confidence interval, we said maybe that confidence interval stretches from 100 to 200. And if we could calculate that confidence interval, right? So the confidence interval is a measure, if its width is a measure of that estimate's precision. And that confidence interval, it'd be nice to interpret it as an interval where the parameter is likely to be, right? Because if the parameter is likely to be between 100 and 200, um, then we would feel confident that we are at least above the national average, that we can make a conclusion that Maine is above the national average. Of course, there was just a bit of a problem with that interpretation. The problem was that that fixed interval would rely on a belief of confidence, right? A subjective belief of confidence. So we had to basically do the same type of procedure but give it a different interpretation. The different interpretation was that 95% of the 95% confidence intervals will contain the parameter. So if I were to create a confidence interval between 100 and 200, over repeated sampling 95% of the time, the parameter would be in there. And since the parameter is not in there, we can conclude, or we have sufficient evidence to conclude that Maine is above the national average. And then we looked at this example of statins and whether or not they should be prescribed to individuals, or at least whether or not there's demonstrated efficacy to individuals who um, may meet some eligibility criteria but do not have the history of cardiovascular disease. And so there were some studies where the confidence interval actually did not cross, indicating that there is efficacy, right? That there is sufficient evidence. Yes, there is sufficient evidence of efficacy. And here we had some studies where there was not sufficient evidence for efficacy based on how we agreed to say yes or no. And so this led to inconclusive evidence, although some of us pointed out that maybe that's not super fair, because if you were to ignore this dotted line, like all of them are relatively similar. I'm just going to say between 0.85 risk ratio 0.85 and zero point 0.9, that all of them are like below 1. And so um, the evidence, and there's no perfect evidence, but if you were to look at the preponderance evidence, maybe that we have enough evidence for some of us to conclude that there is efficacy, even though we didn't have it in any particular study. So this is kind of the gray area that we live in. So, how do we actually go about doing hypothesis testing? And I don't mean the mathematical procedure, because if you were to take a regular statistics class, a traditional statistics class, you would learn procedurally how to do a hypothesis testing. To me, that's less important than knowing the logic of hypothesis testing in and of itself. So, because we have a few clinicians in the room, I wanted to come up with this analogy. It's not a perfect analogy, because it does relate to how you would actually go about getting a diagnosis, like the logic of coming up with a diagnosis. All right, so I'm going to use kind of a analogy. Of course, this is only one way to come up with a diagnosis, so I'm gonna talk about, or I'm gonna kind of relate it to the pattern of a differential diagnosis. Differential diagnosis, right? Um, okay, and so like the logic of differential diagnosis. Okay, so what is a differential diagnosis? A differential diagnosis is simply you're ruling things out. Um, ruling out. You're going to make a list of all the possible diseases, and you're going to systemically rule them out. All right. So what's the disease that I'm going to relate this to? This is actually coming from my wife very recently. So if you were to look at a healthy cornea, excuse me, a healthy retina, so this is a healthy retina, it would look something like this. Of course, there's the optical nerve. If you were to look at a retina that clearly has some disease, so right now we're just going to say undiagnosed disease. Specifically, if you were to look at her retina, you would see kind of these black spots, right? So you can see like there seems to be pigmentation, like there's a big region of pigmentation here in the retina. You see these black spots. Those black spots are called bone spicula. And the most common reason for these bone spicula is a progressive disease called retinitis pigmentosa. Okay, so retinitis pigmentosa, it is a progressive disease. It's a progressive disease. It's the most common reason, as I said. So I'll just it is occurs in both eyes. So binocular occurs in both eyes. And so, my wife, if you were to actually look at her cornea, you would see retina. I keep saying cornea, but if you were to look at her retina, you would see pigmentation right about here. That pigmentation developed when she was a teenager. So she was a teenager. I'm going to put that here. Teenager. Okay. That it developed, but it was non-progressive. Okay, at least now we're in our late 30s, and the region had not progressed. So the question is, well, if this is characteristic of, if these pigmentations, retinitis pigmentosa, and retinitis pigmentosa is progressive, but she's not progressing, like this is not evidence that it is retinitis pigmentosa, right? Like this is retinitis pigmentosa is probably unlikely, especially given that it was only pigmentation in one eye, right? So the retinitis pigmentosa diagnosis as a teenager, they would think that it would progress over time and show up in both eyes, but the evidence was kind of going away from that. So then, what's the next question? The next disease that they thought about? Well, the next disease, because the other thing that could cause it is um, is trauma, right, to the eye. And so what I mean here is like physical trauma. She didn't remember any physical trauma, but because there was no other explanation other than retinitis pigmentosa at that time, um, the leading hypothesis was that it was physical trauma. Except a few weeks ago, she shows up into the emergency room. She shows up into the emergency room, and you could see that there seemed to be in that eye a little bit more pigmentation. That the region of pigmentation had now expanded, getting closer to the optic nerve concerningly. So, what's the explanation for this? Okay, we know that it wasn't trauma. She did not hit her eye. She doesn't remember ever hitting her eye. That would have certainly been felt. So it had to be something else, right? And so now the leading explanation is they had to rule out trauma. So let's rule out trauma. It's not trauma. And the new thing that came up was that our child had hand, foot, and mouth disease. And she, in fact, had hand, foot, and mouth disease pretty severely. Hand, foot, and mouth disease. So she had, the bumps on the hands, the fever. Typically, adults don't necessarily get that. And this is all part of the Kaposi virus or Kalpaxi virus. I don't know how to pronounce it. And this is characteristic of a very, very rare condition called Azores, right? So the leading hypothesis now is that it is Azores. Okay. So I bring this all up because with hypothesis testing, we're essentially going through a differential diagnosis. And unlike in a medical diagnosis where you would you would have a different disease as your first guess, or what might be most likely to occur. In hypothesis testing, your first guess is that results, and this is always true, the results are always are due to sampling variability. All right, so you're finding something in your sample, but the results are simply due to sampling variability. That is called the null hypothesis, right? And we give that H naught. Okay, so the null hypothesis is that results are due to sampling variability, and we have to rule that out. We have to rule out the null hypothesis with sufficient evidence. So we have to rule that out first before we can conclude something else. And whatever that something else is, I'll define in a minute. But this always has to be ruled out first, that it's not due to sampling, or at least it's very unlikely to be due to sampling variability, just as it's very unlikely to be due to trauma, and it's very unlikely to be due to retinitis pigmentosa before we can conclude something else. So let's just say that instead of, now we're going to look at like a drug. So drug A, we want to know whether that drug lowers blood pressure. And so uh, our first group might be taking the drug A, the second group might be taking a placebo. And so the null hypothesis is that any results are simply due to sampling variability, right? So the null hypothesis is that any results, and I'll say results, I will say differences here, due to sampling variability. Any differences in the sample means, so the means between the those taking the drug and those in placebo, are simply the result of sampling variability, but in the population, they are exactly equal. All right. The alternative is that there is some difference, right? So the alternative is that the population average blood pressure for those taking the drug is something different than the placebo itself. But the only way we can get there is by ruling out that it's very unlikely that they are equal, or in other words, of saying that any difference we see in the samples is simply due to sampling variability. So one key thing here is that we never really prove. So we don't prove the alternative hypothesis. Okay, there's always a chance that the null hypothesis can be true, even if we reject it. And that's just inherent in statistics. Everything has some possibility, even if it's low in probability. Okay. So we would just say, if we were to reject the null hypothesis, in other words, if we were to, what you might say, rule out the null hypothesis, we would say reject the null hypothesis. If we were to reject the null hypothesis, all that is saying is that the results are too unlikely to be just sampling variability. And again, this too unlikely is a social convention, how you define that. Now that's socially conceived. That there's no absolute way of actually defining what too unlikely is. So this does not mean that the alternative hypothesis is true. Other explanations, of course, can exist. So this matters because what we say is we reject the null, right? We reject the null, but we did not actually prove a hypothesis, right? We did not come to conclusive proof about a hypothesis. We've simply rejected that the results are due to sampling variability. Okay, so if you were to look at a paper, you would notice that oftentimes people report things like a z-statistics. They might see something like 2.97, z is equal to 2.97, with a standard error of 0.43 and a p-value of 0.001. So what the heck is this z equal to 2.97? Well, what that is, the researchers could have reported like a mean difference, So they could have reported like a mean difference of like, let's just say mean difference. I don't know. Let's say it's a weight loss study. They could have said that the mean difference between those in the intervention and placebo was 17.3 pounds, um, with a standard error equal to, uh, whatever it was. I don't know, 0.43, p less than 0.001. Okay, so they could have done something like this, where they just report the raw mean difference, but you'll notice that uh, they don't usually do that in the discussion section or the results section. Um, what they do is they typically transform it into a z-statistic. So that is called a test statistic versus our sample statistics. The 17.3 is our sample statistic. Okay, so why do we even do this? If we were to look at like the drug study, for example, and we find that the observed difference is 10 millimeters of mercury for systolic blood pressure, we want to know, is this unlikely, right? Is 10 millimeters of mercury, how unlikely is that? Just like here, we would want to know here, is 17.3 unlikely? Well, the problem is imagine you had a study where you just had um, 20 people and you found a mean difference of 10 millimeters of mercury versus a study where you have a much larger sample size of 200, but found the same difference of 10 millimeters of mercury. Well, which one is more unlikely under the null? So in other words, which one would you say you would have, and I will write this, which one would you say that you would feel more comfortable concluding that the results aren't due to sampling variability? Well, sampling variability is really going to be dependent on the sample size, right? So for the same effect, because our sample size is larger for the study B, we would say that study B, it is more unlikely that the results are due to sampling variability, right? So because of the larger sample size, we have results are more convincing because sampling variability is less likely to play a role, right? So here, we don't really have a way, if we were to just report 10 millimeters of mercury, we don't really have a way of saying how unlikely is that value with reference to sampling variability. So we need some way to actually do it. And one way to do it is basically to hold up a ruler to our results and say, how many standard errors are we? How many standard errors are we from the null hypothesis, that they're exactly equal in the population? Okay, so let me give you an example of this. So here again, we have our tuberculosis prevalence in Maine. So here's Maine. And we want to know how many standard errors away it is from the null hypothesis, right? So the null hypothesis is that it's exactly the same prevalence as the national average, so it's over here. So how many standard errors away from it is it? Well, how many standard errors? So we would need to know one thing first. We would need to know what the standard error is, right? So we would need to know what the standard error is, and our standard error goes to about there. And so we can, if this is one standard error, so there's one standard error, we can calculate how many standard errors away are we. So we're 1, 2, 3. That would be 3.4. So we are 3.4 standard errors away from the mean, and that would be z equal to 3.4. Okay, so we're 3.4 standard errors away from the mean. That's definitely larger than 2. And so we're pretty far away in this hypothetical situation. In terms of the blood pressure study, so if you had 10 millimeters of mercury again, you might transform it and you might get a z statistic of 2.45, and you can compare that. So this, in other words, is saying that you're 2.45 standard errors away from the mean. You could compare that across studies of different sample sizes. And so that's why we do these test statistics. So the test statistic is like the standard operating procedure. And you could imagine that a test statistic, just like a sample statistic, it's going to have a sampling distribution, right? But the difference here is that the test statistic sampling distribution, right? So our z statistic, stat, our z statistic is going to have a very predictable shape. It's going to have a very predictable shape. It's going to have a known distribution. Okay. Um, the distribution is the same for all z statistics. Okay. And that's nice. A nice property, because then we can always have some kind of intuitive sense of how many standard errors away that we actually are. All right. So we gain this reference distribution having the same distribution to compare it to. Um, it allows for comparability, and that's what allows us to construct things like a p-value quite quickly. But what we lose is it doesn't tell us if it dropped by 20 millimeters of mercury, the blood pressure dropped by 2 millimeters of mercury, or 20 millimeters of mercury, right? So we lose the clinical meaning of what we are actually finding, or the substantive size of what we are actually trying to find. So with the gain in the standardization, this way to calculate p-values from a table, for example, because of that standardization, we lose the intuitive meaning of the results. So, of course, I will never have you actually calculate a t, and we will get into this. So you should be asking, well, t-test, what's that? We'll get into that in a minute, but just recognize that these test statistics exist because of that standardization. But you don't actually ever need to calculate them because software will actually do it. All right. Okay. So we've talked about this z statistic, how many standard errors away from the mean you are. Typically, you only see that for proportions. Okay. If you have differences of means, so like the mean blood pressure, for example, the differences in mean weight, what's reported is what's known as a t-statistic, and it has the same exact interpretation. The t-statistic also has how many standard errors away you are, but it does have it does have its own little twists and turns. Okay, so what do I mean by that? What do I mean by that? Okay, so what we mean by that is that the t-statistic will follow a t-distribution. So the t-statistic will follow a t-distribution. Okay, so the t-distribution, let me actually pull it up here. So I'm going to pull it up. So the t-distribution is in orange, right? And so what I'm doing here, I'm pulling the slider, and I'm going from a really small study. So like this is like a sample size of 7 to a sample size of 16 to a sample size of 27 to a sample size of 48. You can see that as the sample size increases, it starts to mimic what's in black, which is the z distribution, right? So if I go all the way down to a study of, let's just say 5, you can see that extreme values, right, like we said that two standard errors was really unlikely in a z statistic. But if two standard errors away in a t-distribution is more likely to occur than what you would see in a z-distribution. It has what we call fat tails, right? So extreme values, values greater than 2, are more likely to occur in small studies in this t-distribution. So you might be asking yourself, and this is related to Guinness. I'm not going to get into that, but essentially we can thank Guinness for realizing that in small studies, extreme values are likely to occur. So why is this the case? So remember that the Z is a standardized process. It's just I'm going to just put this, it's going to be our sample mean minus often uh, the true mean divided by our standard error. And remember, our standard error is nothing more than sigma. So that's our population standard deviation divided by the square root of n. All right. So what I wanted to turn your attention to is that the z statistic right here has the sigma in the denominator. Okay. So in other words, what it means, that means is that we have something that's proportional to. So I don't want that. We'll do proportional to 1 divided by sigma. Okay, so it's proportional to 1 divided by sigma. That sigma is our population standard deviation. Okay. So the problem is that we often don't actually know what this population standard deviation is. The best we know isn't the population standard deviation. The best we know is the sample standard deviation, right? So we don't know the population, we only know the sample standard deviation. So what does that mean? It means that we have a test statistic that is proportional to 1 divided by the sample standard deviation. It turns out the sample standard deviation in small samples is going to be an underestimate. What I should say is that in repeated samples, for small sample sizes, this sample standard deviation is really going to be quite small, right? It's going to be quite small with small sample sizes. And the way you can think about that is that most of your samples are going to be in the middle. You're going to see a lot of homogeneity. You don't have the opportunity for extreme values. And so, on average, in small samples, your sample standard deviation is not going to be very spread out. And that leads to an inflated z statistic, right? Because if this is small, it means that our z statistic is going to be inflated, okay? So if our z statistic is inflated, that's what leads to, so this is basically saying that our z statistic needs to be larger. That's why it's orange and it's greater than 2 more frequently, to account for the fact that in small samples, very frequently we're not going to get a large enough standard deviation. And so that's kind of the intuitive explanation. I don't know if that's helpful, but that's where it comes from, that the t statistic really is when we substitute the population standard deviation with the sample standard deviation. We need to account for the fact that the z is going to need to be inflated, and that's what this t statistic does. So let's go ahead and talk about p-values. So p-values, we have to ask ourselves if the null hypothesis were true. So in other words, if results are just sampling variability, that is the underlying first diagnosis in our sample, that is just the result of sampling diagnosis. It's, that is our null hypothesis. That's our presumption that things are just the result of sampling variability. How often would we encounter a result that is that extreme or more? And the sampling and the p-value is just the probability of observing that extreme of a result. Okay, that makes no sense unless we go back here. So here we go. So I'm going to go ahead and going to erase this. Okay. So we said that the p-value is, here we had our sample statistic, right? And we want to know how, if we want to calculate a p-value, we want to know, if we want a p-value, the p-value would be, what is the probability? It's answering the question, what is the probability? Is the probability of observing an event as extreme or more extreme as what we observed in our sample. Okay, assuming the null hypothesis, so H naught, is true. All right, so our assumption that the null hypothesis is true is why we put this standard, this sampling distribution centered at the parameter value, that there would be no difference. So our null hypothesis here is that there is no difference in Maine's prevalence compared to the national average. So if that null hypothesis were true, we would expect sample prevalences to generally be in this purple shaded region. We found something that was pretty extreme, way outside. And so the p-value would just be how extreme we found a result that is as extreme as this or more so. So like we could even go all the way out to the right. And we actually do it both ways. So in order to calculate a p-values, we would take this result and we would multiply it by 2. So we take that area, then we would multiply it by 2. And what that is doing is it's saying, well, it could be extreme from the right side, or it could be as extreme from the left side as well. Okay, so as extreme or more. The probability of observing an event as extreme or no more, assuming the null hypothesis is true. All right. So if we see a p-value of 0.016, so if the difference we observed was just due to sampling variability, assuming the null hypothesis is true, right, we would see the result this extreme in only 1.6% of the time. Okay. Oh, so I did it here. Okay. Okay. So as I said, we multiply that result, so that extreme value, by 2. That's because what we typically do in research are two-tailed tests. There are one-tailed tests, but we never actually really see it in standard practice. So in reality, you would learn about it in a introductory statistics class, but they don't really show up when it comes to actual research. Why that doesn't happen, I'm going to go back to, that's because our decision making is a social convention. We just have norms that we follow. And sometimes that gets us in trouble. All right, so what p-value, what are some common ways of some common misconceptions of a p-value? So the first one is that the p-value is the probability that the null hypothesis is true. Okay, so it's not. We are assuming that the null hypothesis is true, so you're assuming sampling variability. And then we're going to calculate the probability of observing what we actually observe, right? So the courtroom analogy is, if I'm innocent, what's the probability of this evidence, right? So the presumption of innocence, what is the probability of this evidence? Not, given this evidence, what's the probability that I'm innocent, right? So that's not how our justice system is supposed to work. Okay, it's supposed to, the presumption is innocence. What is the probability? Um, what is the probability of observing this evidence? The second is that the p-value is not the probability. Your result is due to chance. Okay, so all results involve sampling variability. That's inherently in sampling. If the results were just sampling variability, how often would you see data this extreme, right? So if it was just sampling variability, how often would you see this data as extreme? Okay, so it's not just due to chance; it's just sampling variability, because chance can have lots of other connotations to it, but we're narrowing it down to just sampling variability. And the third is, a small p-value does not mean the effect is large or significant. Okay, so we will get into this, but you can have a very small p-value and a tiny effect, right? So it's totally possible that a you could find a difference in people's blood pressure of zero point 0.1 millimeters of mercury, which is minimal, with a sample size. You would find that if you had a sample size in the millions, right? So if you had a sample size in the millions, right, 1 times 10 to the 6, you would find that this is statistically significant. Obviously, that's not clinically meaningful, okay? But that's just the result of the fact that the standard error, or precision of our estimates, gets increasingly precise with large sample sizes. So that puts um, large studies at a relative advantage, because typically in publication, we hyper focus on this p-value. Um, that seems to be a gateway, more so than the clinical meaningfulness of something. Okay, and that gets us into trouble as well. All right, so the null versus alternative hypothesis, from p-values to decisions. So we've learned that when p is small, we reject the null hypothesis. So we just simply reject. That doesn't mean we accept the alternative. So it doesn't mean that we've proven that the drug actually work. Okay. So what does the rejecting the null actually mean? Well, it just means that we assume that the null is true. We found that the data was very unlikely given our assumption, right? So only 1.6% of repeated samples would have a result at that extreme or more. And so we said that that was sufficient evidence to reject the null hypothesis, that it's just too unlikely given our norms and conventions. But of course, it's not impossible, right? So it doesn't prove that the alternative is true. Of course, there's a bunch of other reasons that could explain, because we just were talking, we assumed that it was the result of sampling variability, but it could be a bunch of other things. It could have a placebo effect. It could be selection bias, so you happen to have a group that had healthier participants. There could be systemic errors in blood pressure measurements, if machines aren't calibrated correctly and you do things at different sites. There's a host of other reasons of actually um, of other reasons why the null hypothesis could still be true. So our null hypothesis still could be true, but we rejected the null hypothesis. Okay, everything is possible, even if it's not probable. So what does this mean? Well, we try to be very careful with our words when describing conclusions. Um, Rejecting the null hypothesis, or we fail to reject the null hypothesis, as opposed to accept the alternative. So that we don't want to say, because that's just too close to saying that the alternative is true. Or we accept the null hypothesis again. Um, historically, somebody decided that, again, that language is saying that the null hypothesis is too close to saying that the null hypothesis is true. Of course, we don't say that a study proves. We might say that it is consistent um, with some other explanation, or that the data suggests, or that the evidence supports, right? So we want to be careful of overstating our claims, given that everything is possible, even if it's not probable. And these are some of the words that have become accepted in how we communicate that. All right. So good. Our results are consistent with, our data suggest. Of course, you don't want study proofs, or we've demonstrated that, right? Um, without uh, some some kind of acknowledgement that that the alternative hypothesis still could be false in reality. All right, so I'm going to skip that. So we've said everything is possible, even if it's not probable. Okay. So I'm going to bring up this very famous box. So the reality is the reality of the world, that the null hypothesis, let's just start here, the null hypothesis is true. The other way you could say that is that uh, uh, mean differences are zero, right? So the mean differences is zero in the population. Can I do that? Huh, I wonder why it does that. Oh well. Let's just do this. So the mean difference, I will go ahead. Mu. So we're going to say the mu treated is equal to the mu control. And then this one would be that they don't equal. So mu treated does not equal mu control. So that's reality. Of course, and that's our null, H naught. Of course, we're going to make decisions based on the data, okay? So the first decision that we could make is that we reject the null hypothesis, that we reject this. And if we reject the null hypothesis, but the null hypothesis is true, then, well, in that situation, oops, we don't want that. In that situation, we have created an error, right? So this is problematic because we've rejected the null hypothesis when the null hypothesis is true. If we were to reject the null hypothesis and in truth the null hypothesis is false, that there are differences, that's actually a good thing, so that's good. Similarly, if we fail to reject the null hypothesis, we do not reject the null hypothesis, and the null hypothesis is true, we've also made a good decision. There's no error in that decision. But if we fail to reject the null, but the null hypothesis is false, that also is a problem. Okay? So we give each of these errors names. The one I want you to focus on right now is this type 1 error. We'll talk about type 2 error when we get into power and sample size determinations. But type 1 error is when we've decided that we have sufficient evidence to reject the null hypothesis, but the null is actually true. That is type 1 error. We often call this a false positive, right? So false positive because the positive means you found a positive result. In other words, you found something that's worth publishing, and that actually was just by chance you got a p-value. There, I'm using the word. You were part of that. So we have our sampling distribution, and you might have got a p-value of 2 point, z statistic of 2.0, so this was 2, and so your p-value was equal to 0.049, right? But this is just, that value could have just been sampling variability. So let's like imagine this. So let's say we had 20 ineffective drugs, okay? So literally, you are a researcher and you're just trying to mess with people. So you dispense 20 ineffective drugs, right? So these are just placebo drugs, and you are making the claim that these drugs are effective, right? Even though you know for a fact that they aren't. So you convince people to go out and test them for whatever it is that you're saying they are effective for. The question is, will any of those drugs actually get published as being effective? Okay, so we know that they aren't because they're just placebo drugs and we're just messing with people, but somehow we've convinced people that they could possibly be effective because we've mischaracterized it. And the question is, what percentage of those drugs would get published as effective? And you're probably saying to yourself, well, hopefully none of them would get published as effective. But it turns out that because everything is possible, even if it's not probable, and because we're using a benchmark, so this alpha is equal to 0.05, means that we're using that it's outside of the 95% interval, that 1 out of 20 will exhibit a p-value of less than 0.05 just because of sampling variability. So even though we know the drug doesn't work, we will have 1 out of 20 that will show up as a false positive. So we call this 1 out of 20, this 5%. Again, that 5% is because we're using 95% confidence intervals, right? Or we're using a threshold value that would relate to a 95% interval in our reference distribution. It just means if we test many true null hypotheses, we will incorrectly reject about 5% of them. That's what the type 1 error is. If we go to 99% confidence intervals, so 99% confidence intervals, okay, if we go to 99% confidence intervals, that means that our alpha will equal 0.01. And that means that we would only reject 1%. So as you increase your confidence level, you're going to decrease your type 1 error rate, that false positive. So what implication might this actually have? Well, let's think about this. So in 2012, a very famous paper published in Nature was published. So what they did is they took 53 landmark studies in cancer biology and they tried to replicate it. But only 6 out of 53 actually replicated, which means that 47 out of 53 failed to replicate. So what I want you to think about is how might type 1 error contribute to the replication crisis in biomedical research. And of course, this isn't limited to biomedical research. It's actually even a bigger problem where I fail in psychology. So psychology's replication crisis is an even bigger issue. But how is it that type 1 error and our social conventions for how we decide on publishing research, how we have identified the gateway to getting published with p-values, how has that contributed to the replication process? And we will pick up on that in hour 2. Thank you.